We saw that we could see through cardboard and foam. So here is a box, and a cardboard box with some stuff in it. It's got a bunch of foam peanuts, and it also has a plastic knife and a razor blade. And this is the terahertz image taken through the cardboard. There are a lot of security applications. As Dan mentioned, terahertz radiation can go through cloth, and we saw that it went through a bandage. This is a picture of stuff inside of a suitcase. One application that people would like in the security field would be to be able to see if somebody is carrying a concealed weapon or a concealed bomb. That's actually a very difficult problem. That's quite a very difficult problem. Okay, there's another company called TeraView, and so this is a completely different set of applications. This is a pharmaceutical application. I don't know about you, but I always get a little nervous when they say, the pharmacist tells me, well, we're going to give you the generic instead of the brand name drug. You wonder if what's really inside that pill. And using terahertz radiation, you can actually see if the actual active ingredient is in there. Now, this is something that's being used by pharmaceutical companies as sort of for testing batches, because obviously you're not going to do that for every pill. But this is a real-world application that pharmaceutical companies are buying terahertz instrumentation for. In medicine, it's extremely useful to be able to see with the entire electromagnetic spectrum. This is a photograph of a visible photograph of a tumor on the skin of a patient. And normally a surgeon will have to, won't be able to know the extent of the tumor. You can't tell by x-rays. But on the right is a picture taken using terahertz radiation that shows the extent of the tumor underneath the skin. And this is work from a local group, Elliott Brown's group, where they're imaging a burn on artificial skin through 5 and 10 layers of gauze. Okay, so those are some of the emerging applications of terahertz radiation. And now I'd like to tell you about some of the frontiers of terahertz science that are being investigated at UCSB. So Phil Lubin, who lent me the camera and who's in the audience, he likes to take baby pictures of the universe. Okay, so let me explain what I mean by that. If you take a picture of the sky at terahertz frequencies, you can see back in time to what the universe looked like when it was only 300,000 years old. Now it's 15 billion years old. So it's an incredibly valuable and powerful and exciting tool to study cosmology and the origin of the universe. He has to fly his instruments on balloons, and that's a picture of a balloon launch. This is from Mark Rodwell's group. He's in the electrical and computer engineering department. This is a transistor that can turn on and off electricity 0.3 trillion times a second. So the frequency of turning on and off electricity is 1/3 of a terahertz, and they have a plan to get up to a terahertz. So we're going to have electronics that operates at 1 trillion hertz in the next few years. This is some of my research. So one of the things that we really would like to do is to have sources of terahertz radiation that are sort of like this laser pointer. So a source of terahertz radiation that would emit a few milliwatts and that would operate at room temperature using a battery. Well, right now, this is very far from reality. But there's a very exciting development, which is that there are solid-state terahertz lasers. They need to be cooled down in a cryostat that's something like this. And so what we want to do is to make them so that they work at room temperature. So what we're doing here, and with some of my students who are in the audience, is we're designing atoms, artificial atoms that emit at terahertz frequencies. So we call these posts, quantum posts. Here's a picture from a top view. So this entire picture is about the size of one red blood cell. It's the area of one red blood cell. And this shows a large number of these quantum posts that are artificial atoms for terahertz frequencies. This is a cross-sectional view. This picture was taken with a microscope called an atomic force microscope. These are way too small to see with even a powerful optical microscope. This is a picture taken with a electron microscope, cross-section, showing that these artificial atoms are sort of shaped like truncated cones. And this is a theoretical calculation by a colleague of mine, a coworker in Iowa, which shows how the electron density in a quantum post looks when it's in its lowest energy state and when it's in a higher energy state. And if an electron decays from this state to this state, it will emit a 4 terahertz photon. Very much in the same way that the atoms in that lamp that was emitting some of the colors and that emitted the ultraviolet light, that real atom emits visible light. This artificial atom is going to emit terahertz light. Okay, so now I want to talk a little bit, do one more demonstration here. At the conference, one of the hottest topics actually at this conference was water, was the terahertz absorption of water. So let's see how terahertz does. Let's try to see how terahertz does at going through water. So we've got the bandage on the front, and now Ben is going to he's got an eyedropper there. You can see the eyedropper in the screen. He's just going to put a few drops of water onto this bandage. So that was how many drops?
3 drops.
That was 3 drops. Okay, so put on a couple more. That was 6 drops. So he's lifting up the bandage to put on the drops. And now, well, it's negative. That's just a fake number. That's noise. So just a few drops of water on the bandage completely absorbs, as far as we can tell, completely absorbs this terahertz radiation. Well, actually, it doesn't absorb it completely. It's just that this tabletop source is not powerful enough to go through the wet bandage at this frequency. Well, a tenacious graduate student, Jing Shu, who you saw earlier, that's the repeat of that picture, really wanted to measure quantitatively how much water absorbs at terahertz frequencies. And so what she did is she used our very, very bright terahertz source and the free electron laser and a detector essentially identical to the one that's on the table to make a very accurate measurement of the amount of transmission through water. She did this by using the powerful source, the sensitive detector, and spending a lot of late nights in the lab. So this is a graph which shows how much water absorbs as a function of frequency. So if a bigger number means that it absorbs more. it attenuates more. And you can see that at 2 terahertz, well, Jing's, so the measurements that were done at UCSB are these red dots. And then these other points that are kind of scattered around it are measurements that other groups have made of the transmission of water. So we have these very accurate measurements that were made at UCSB, and this, I think, is an indication of the state of the field that at this point we're able to publish in 2006, Jim Allen and Kevin Plaxco and Jing Xu were publishing the absorption spectrum of water. Well, why do we and why do the people of the conference so excited about water? Water by itself is a fascinating substance. It's an extremely complicated liquid. But of course, the real reason that people are interested in water is that water is what we are made of, 95% or so. The rest of what we're made of, a lot of it, most of it, is proteins. Proteins are the microscopic machines, the tiny machines that regulate our metabolism. Proteins are responsible for initiating vision, transporting oxygen from our lungs to the rest of our bodies. And there are tens of thousands of proteins in your body. Now, water is their native habitat. So, like the machines that you're familiar with, proteins need to move in order to perform their functions. And actually, a lot of biologically relevant motions occur at terahertz frequencies. We want to understand these motions, and there were some beautiful talks at the conference by other researchers also talking about protein dynamics. So we have a large collaboration here which is studying protein dynamics using terahertz absorption and terahertz electron magnetic resonance. This was funded by the W.M. Keck Foundation. There's a picture of a protein called lysozyme, and that protein is moving, and it's moving at the motions that you see are slowed down. This is a theoretical calculation. Of course, we couldn't see the motions if they were in real time. This is a theoretical calculation of how this protein moves, and in fact, those motions are at terahertz frequencies. So we're embarking on a project to use terahertz radiation to film proteins in action in their native wet environment. This is a really challenging project, but we're very excited about it, and we look forward to telling you about it in the future. Thank you for coming.